Hey everyone, today, this video is going to be a little different, simply because, as you can see, I don't have my marker and or expo marker, whatever, if you will, on hand, simply because today's video is going to be a recap video and I'm going to do these types of recap videos every few episodes, just so that you can refresh your mind upon the subjects that we've covered. So yeah, today we're going to be going over what we have been doing over the course of these 7 episodes. So why don't we get started? We started off with matrix notation. I established this matrix A, where the bottom here, A and B, A is equivalent to the amount of rows in that matrix. In this case, there are 2 rows, as you can see, and B in this case would be equivalent to the amount of columns, within that particular matrix, and there are 4 in this case. They can equal any natural number. And in order to specify a specific location within this matrix, you can describe it in this notation. So I guess to say it orally, the segment here is what matrix it is. In this case, I classified this as matrix A. And this section is, you can, as I said in that episode, you can think of it as a coordinate pair, if you will, on a 2-dimensional plane. If you graph, you've definitely ordered pairs. If you've graphed points on a number line, on a 2-dimensional plane, which you definitely have if you're watching this, then you can relate to this. And you can relate to this as just a coordinate plane, except in this case we're thinking in terms of rows and columns. So the first term here symbolizes, this would usually be x, but in this case it symbolizes rows, and the second term, which would usually be y in Cartesian coordinates, would symbolize b, or the amount of columns in here. And this ordered pair, as we'll call it, points to the point F in this matrix. Hopefully that explained a little better than I did in that episode. So here's another example using real natural numbers. B, we classified this as B, completely random, by the way, and we just made this a 3 by 5 matrix, so 3 rows, 5 columns, and we wanted to pick out this point 1, and as you can see, this is in this matrix B, 3 by 5. This point is located on the second column, the second row, and the 4th column, as you can see here, and that's equivalent to 1. What else? Here I seem to be actually giving examples of square matrices. Actually, these are square matrices. No, what I was doing here was I was explaining how, in order to add or subtract matrices, the amount of rows in the columns have to be equivalent. This is different in matrix multiplication, but I'll get to that soon, once we get there. So yeah, here we added 2 matrices, A and B, both 2 by 2, so I think that's good enough for that. Let's continue to matrix subtraction. This was relatively simple, so I won't spend that much time on this, but basically it's the same concept as matrix addition, as we worked on in the matrix notation section, which also included matrix addition. But here, instead of adding the matrices, the terms within the matrices, it's the same rule, by the way. They have columns and rows have to be equivalent to each other in both matrices. So both of these, if this one's 3 by 3, this one also has to be 3 by 3. If this one's 2 by 3, this one also has to be 2 by 3, etc. but instead of adding the terms, you just subtract the terms. Find the difference of the terms. So I think that makes sense. I just did a few examples here. We used alpha and beta just for grins. Okay. Matrix multiplication. Here, we established an important rule. The amount of columns in the first matrix always has to be equivalent to the amount of rows in the second matrix. So as you can see, if A is equal to a 2 by 3 matrix, B has to be equal to a 3 by n matrix. And the reason I put n at the end is because that can be any number, but in this case it's 2, just for convenience, like I've stated numerous times. Matrix multiplication is not commutative in that A multiplied by B is not equivalent to B multiplied by A. We'll try a few examples. Let's see. So A multiplied by B, here we did it. We wrote it out first. It's usually a good strategy. And then we used dot product. This requires dot product multiplication. So the row information here gets its information from B's column info, and the column info gets it from the row information. So that's that. And we multiplied by, you always go down the column and or row by multiplying. You don't alternate the row until you've multiplied the row by the last column, and then you finally alternate the row, and you repeat the process again with the columns. And then you can see this process here. If you don't understand what I just said, which would make sense if you haven't watched the past videos on matrix multiplication, then I would highly recommend for you to go back to review that. Here we just simplified everything. Nothing on the back. Let's continue. Let's see, these are just some more examples of matrix multiplication. I assume that I don't have to review this. If you want to review this, then just go to the past episodes on this. I assume this is either the introduction to matrix multiplication or the introduction video, or the examples on matrix multiplication, but you can see for yourself. Assume it's the examples, but yeah. Anyway, we now switch to the the purple realm of these episodes. This is inverting matrices. Inverting matrices is only applicable if they're square matrices, in that the rows and the columns in one matrix have to be equivalent. So we called this alpha. Yep, I also, if you want to see it here, I wrote it down here. So this is written with a negative to the negative first power. I'll talk about that later in the identity matrices, you should go back to that. I highly recommend that video. Actually, I'm quite happy with that one, so you can see that one if you want. So I just did that example there. We learned what a adjugate and a determinant is, which is really important to inverting matrices. Again, the determinant is just the A and D term minus the B and C term. The difference of A and D and B and C. Well, in a 2 by 2 matrix, that actually only applies to 2 by 2 matrices. We'll get to that in future episodes. On 3 by 3 matrices, it's a little different. Here we just, this is actually looking into the future. Okay. Oh, I think I wrote this on the back. Oh, this was actually, I wonder where I put my 3 by, remember when we did that 3 by 3 matrix? I wonder where I put that. That was the colorful one. I wonder where that one could be. Here it is. Let's go to this one real quick. Running low on time, so multiplying two 3 by 3 matrices. I'm not going to stall too much on this one. It's just multiplying matrices. You can go back to that video. Also, you probably barely see it with the lighting I've installed right now. It's dark outside at the moment. See, this was the second part to that. That's not important. I wonder where, oh, identity matrices. Okay. This one was one of my favorites. So identity matrices. Identity matrices can be compared to the identity law on natural numbers, integers, or for that matter, real numbers. For example, a multiplied by a's inverse, which is 1 over a, or a to the negative first power, as you can see here. Because if you don't know it, if you don't know what negative roots are, basically, for example, if you have 3 to the, for example, negative fourth power, that's equivalent to 1 over 3 to the fourth power. So you can work that out yourself. Essentially, it's just, they don't result in negative numbers. That can be misconception amongst people who don't know what negative roots are, or just, negative powers. So yeah, it's just actually, it always appears as fractional. Unless there's a minus sign that's on brackets against that number, but that's beyond the point. Anyway, identity matrices can be compared to the identity, or sorry, this was the inverse law. This wasn't the identity law in amongst real numbers, because this is A inverse, right? And this is just analogous to inverting a matrix, because if you, as we'll explore in a second, if you invert a matrix and multiply that inverted matrix by the original value, in this case A, and we use that analogy here, or did we? Yep, this was our matrix. This is an purely analogy. If you multiply it by its inverse, then it becomes the identity matrix, which is this. If you need more elaboration upon that, you can go back to that episode. It's just the episode before this one, and on the back, we multiplied our original matrix by the inverted matrix of that same matrix, and what do you know? It resulted in this, which, as you saw beforehand, is an identity matrix. So you're correct here. Anyway, that's about it for now. I will be uploading another video tomorrow. So thank you everyone for watching this. Hopefully you enjoyed this episode. It was just a recap of everything. It really wasn't important to watch if you understood everything from now on, but it's just nice to wrap all the info up in a nice package, and just, I don't know, remind you if you've forgotten. So thank you everyone for watching. Have a nice day as always. Bye bye.